Morning everybody. Today I'm going to be doing my presentation on plasmonic solar cells for 4x03 Intro to Photovoltaics. So just to kind of describe the flow of this presentation, we're going to be talking about our agenda. So first of all, I'm going to introduce the idea of plasmonic solar cells and the basic principle behind it. Then I'm going to talk about sustainability. Why do we care about plasmonic solar cells? How do they make things better for us, and what's their advantages over our standard silicon cells? Then I'm going to be discussing the physics of operation, where I'm going to delve into the details of how they actually work, physics behind them, and how they increase efficiency or reduce price, whichever the advantage is. Finally, I'm going to be discussing the manufacturing process to produce plasmonic solar cells, discuss its feasibility, and finally, I'm going to summarize my presentation. So just to introduce what plasmonic solar cells are and how they differ from standard solar cells, is that in general terms, what happens in a solar cell is that you have light wave, it hits the semiconductor, and then you have electricity generated. The difference now, if you look at the PowerPoint slide, is that we have nanoparticles, which are these balls over here, on top of the semiconductor. So when light comes and hits the nanoparticles, what happens is these nanoparticles actually scatter the light forward into the semiconductor. And what happens is now light is trapped between these nanoparticles and the substrate. So it keeps moving through the semiconductor over and over again, as you can see here. What this is doing is it's increasing the absorption of the semiconductor. The more times light is going through the semiconductor, the more electricity we can generate. So to better understand the physics of the plasmonic solar cells and to gain some appreciation of the technology, we first need to look at the history of the main scientific process that operates it, which is the surface plasmon resonance. This began in 1902 with Dr. Wood at Johns Hopkins University in Baltimore, USA, when he observed that when polarized light was shined onto a metal-backed diffraction grating, a pattern of light and dark bands appeared in the reflected light. Although he couldn't explicitly describe the phenomenon, it was the backbone discovery for more research to come, and for that he's considered the father of SPR, which is surface plasmon resonance. It was later in the 1950s when Pine and Bones picked up the research. They experimented on electron energy losses in gases on tin foils. They hypothesized that these losses were a result of electron excitations, creating plasmon oscillations. In other words, the excitations resulted in surface plasmon oscillations, in which there was reflected electric field from the surface of the metal particles. Later on in 1968, Otto demonstrated that by using attenuated total reflection, the surface waves can be excited. Simultaneously, Kretschmann and Rather achieved similar conclusions using the attenuated total reflection method. Later on in the 1980s, many papers came out describing the light scattering effect. SPR and other techniques utilizing evanescent waves were applied and integrated in thin films. Now, with the knowledge of the history of this beautiful technology, we can talk more about the sustainability, the physics of operation, and the manufacturability of it. In terms of sustainability, I think the most important thing to talk about is how can we make it comparable to oil prices or fossil fuels. And to do that, we actually need to reduce the price of solar cells, of energy generated for dollar money, by at least 5 times. So how does these plasmonic solar cells contribute to making the price cheaper? Well, the way plasmonic solar cells work is that they use thin film, and we are going to jump into more details on that in the physics of operation. But what you need to know for the sustainability aspect is that plasmonic solar cells are 300 times thinner than regular silicon solar cells. 300 times thinner. And what's important to talk about is that 40% of the price of solar cells is in the silicon wafers. So the silicon wafers make up 40% of the price of silicon solar cells. So the fact that we can reduce the amount of solar wafers used by 300 times reduces approximately 40% of the price. What sacrifice happens as a result of this? Well, the efficiency is marginally lower. We reduce the efficiency to 18.5% from 22%. But considering the 40% increase in reduced price, or the 40% reduce of price, this is a very good compromise. And so now that we understand why we're doing this and the motivation behind it, let's talk about the physics of operation. So in terms of the physics of operation, there are three main ideas that we really need to consider when we're designing a plasmonic solar cell. First, to understand why we would design things that way, we need to talk about what light is. Light, at the end of the day, can be thought of as an electromagnetic wave that has a certain frequency and has a certain wavelength. So when we're designing plasmonic solar cells, we know that there's something called plasmonic resonance, which means that the electrons on the surface of the nanoparticle vibrates or oscillates at a certain frequency and creates a certain wavelength. When we would like these two things to match, the light frequency and wavelength, to maximize scattering. The third design property is the position of the plasmonic solar cells. Where we place our plasmonic solar cells heavily affects the way light is going to scatter into the semiconductor. And we're going to describe these three design principles in more details. Okay, so let's talk about a little bit about the wavelength and why it's an important property. Basically what happens is, on the surface of a metallic surface, you have these electrons, free electrons, and these are called surface plasmons. What happens is, when light hits the surface plasmons at a specific with a specific frequency and wavelength, these surface plasmons start oscillating or resonating, also producing electromagnetic wave that has a certain frequency and a certain wavelength. What we want to do is, when that wavelength is near plasmon resonance, then the nanoparticles will scatter a great amount of light. And this can be seen by the formula of C scatter, right? It's based on the wavelength. It's also based on the polarization of the material. Polarization is alpha over here, and it's based on the volume as well as the EP and EM. EP is the dielectric function of the particle, and EM is the dielectric function of the embedding medium. I'm not going to go into details about EP and EM because they're out of scope for this course, but the volume is chosen to be a sphere because that would maximize polarizability. But what we can draw is a particular relationship, which is when EP is equal to -2 EM. If that's the case, EMs will cancel. You will get -2 plus 2, which is 0. If you have 0 in the denominator, alpha approaches infinity. If alpha approaches infinity, then your scattering will greatly be increased. So the important relationship is, again, EP equals or approximately equals -2 EM. When that relationship is met, we call that the surface plasmon resonance, SPR. Why is SPR so important is because when we have SPR, surface plasmon resonance, then the surface plasmon resonance, then the scattering cross-section well exceeds the geometrical cross-section of the nanoparticle. And this is important because the nanoparticle might be 100 nanometers in width, while the light wavelength is 900 nanometers in width, 9 times greater. And we want to match those two wavelengths. So we want to produce an electromagnetic wave that's 9 times greater than the width of the nanoparticle. So that's why surface plasmon resonance is such an important concept, and it's based around the wavelength of light. So another important design principle is going to be the frequency. And us as designers of a plasmonic solar cell need to understand how we can use the concept of frequency to maximize light scattering and therefore absorption. So we know that when light hits the surface plasmons, they start resonating at a certain frequency. This is called the surface plasmon resonance frequency. Now, when the SPR frequency is near light frequency, light scattering is maximized. If we look at the equation over here that describes the frequency we get, well, it's based on N, which is the density of free electrons, E, which is the electronic charge, M is the mass of an electron, and epsilon naught, which is the free space dielectric constant. What we notice here is that out of all of these, the only thing we have control over is N, which is the density of free electrons. And so we have to choose materials that have high density of free electrons. These materials include gold, silver, aluminum, and copper. And the more popular choices are gold and silver because they're more reliable. They maintain their properties over time, so they don't have to be replaced as often, and they can withstand the the test of time. Now, we know that if we maximize WP, omega p, we increase alpha. Alpha, which is the polarizability again, and if we increase is based on omega p. If omega p goes up, alpha will go up. And if alpha goes up, we know from previous equation that we looked at describing the wavelength, as alpha goes up, the scattering effect also increases. So this is a win-win. So as plasmonic solar cell designers, the third design principle that we need to consider that affects the physics of operation is going to be the position of the nanoparticle from the semiconductor. If we look at the figure number 3, and we look at B over here, well, we notice something interesting. We notice that we have a particle 20 nanometers away, which is going to be the blue particle with the blue light pattern. And we have the 16 nanometer particle away, which is the red nanoparticle. The red nanoparticle being further away, there's going to be less light overall radiated into the semiconductor. But that light is going to be at an angle greater than the critical angle. The angle being greater than the critical angle means that there is more transfer of energy from light into the semiconductor. While the blue particle, which is closer to the semiconductor, is going to have more light go into the semiconductor, but less light at an angle greater than the critical angle. So there is a compromise between the position that we have to choose. And now if you look at figure 4, which kind of summarizes what I just said, the bottom here is distance from the substrate. And as we see, as the distance from the substrate is less, the fraction of scattered light into the substrate increases, which means we have more light being scattered forward into the semiconductor. As the distance increases, then the relative scattering cross-section increases, which means we have more light traveling at an angle greater than the critical angle into the semiconductor. Plasmonic solar cells, after doing some research, it seemed like the top-down approach for creating and manufacturing nanoparticles was the method of choice for the plasmonic solar cells, which means that you have big particles and you grind them down into nanoparticles. How the technique that's used in plasmonic solar cells is high energy ball mills, and they're used to grind down materials. If we look at the image down here, we actually get a better idea of how this operates. You have the nanoparticles that are, well, you have the material that's big go into the centrifuge milling bowl. The bowl would rotate counterclockwise. As the ball rotates counterclockwise, you have these high energy balls inside that are usually made of steel, and they rotate in the other direction. They rotate in the other direction, and what happens is the friction that is caused between the rotation of the milling bowl and the high energy balls grind down the material into nanoparticles with the minimum size of course is 26 nanometers. And what's interesting is that the shape of these nanoparticles is homogeneous at the end, which means they take good circular shape that can be used on the surface of a metal. I'm going to summarize everything we've talked about so far. First, we discussed the history, all the way from Dr. Wood in 1902 to the 1980s, when we were getting research papers on SPR technology, and as well as getting models of plasmonic solar cells. It's important to understand the history to appreciate the technology. After that, we talked about sustainability. Well, why do we care about plasmonic solar cells? Why are they better than normal solar cells? And how do they make things, whether more efficient or cheaper? And we talked about why they make things cheaper. Then we talked about the physics of operation. Physics of operation comes down to the main concept, which is surface plasmon resonance. The fact that these free electrons on the surface resonate at a certain frequency and wavelength and produce that wave back into the semiconductor, so we can have more absorption and more light scattering in the semiconductor. Then we talked about the manufacturability. Well, we talked about the top-down approach that's used to create nanoparticles. And we talked about these high energy ball mills that are used to grind down bigger materials into nanoparticles that can be used for surface plasmon resonance. Thank you so much for watching. I appreciate it.